Hello, I'm going to be deriving the equation for the moment of inertia of a shelled cylinder. So let's start by drawing a shelled cylinder. It's going to be of length L, have an inner radius of R1, and an outer radius of R2. So it is going to be a hole through it with a radius R1, and the rest is going to have a radius of R2. So let's start by writing our equation for the moment of inertia. I equals the integral of r squared dm. Now we know that dm over dv, where dv is volume, equals m over v. So now we are going to say that v for a cylinder is going to be pi, and now something squared, it's not going to be r squared, times L. So what is this R? We can't just say R because it's not. There's a hole in the middle. So we have to realize that the R squared is representing the circle. So for this, it's going to be R2 squared minus R1 squared. So that's going to give us our constant volume. So now we can rewrite our equation for inertia. I equals the integral of R squared times, and then if we multiply by both sides, we can cancel the dv here and get dv here, and we can replace the dm with m over v dv, and then dv, we know that v equals pi r squared times L, and this r is lowercase r, that means it's variable, that means it's what we're going to be integrating upon, so I do put it lowercase, I don't put it in this form. We only did that because we were working with constants. Now I take the derivative of both sides. I get dv equals 2 pi r L dr. So now substituting that in, we have I, and I'm also going to substitute in the v here from the v here. Not here, the v here. And I'm going to get I equals the integral of r squared, m over pi r2 squared minus r1 squared times 2 pi r times L times dr. So we're going to immediately cancel, there's also an L I didn't include here. We're going to immediately cancel the L's, we're going to immediately cancel the pi's, and then we're going to bring everything that is a constant outside of the integral. So we have I equals 2m over r2 squared minus r1 squared, and then we are going to define our limits of integration. So we're integrating from R1 to R2 because we start at R1 and then we go out until our radius equals R2. So R1 to R2, and these R's combine to give us R cubed dr. And then evaluating this integral, we're going to get equals 2m over, and then of course R1 squared minus R2 squared, and then r to the fourth over 4, evaluated at r2, r1, that's just the integral of r to the cubed. And then let's evaluate that at r2 and r1, 2m over r1 squared minus r2 squared times r to the fourth, r2 to the fourth, minus r1 to the fourth, over 4. So that's just plugging in our values of R2 and R1 and subtracting them for this. So now what we're going to do is we're going to rewrite this as a difference of squares. So we should know that we can write this equals 2m over R1 squared minus R2 squared times R1 squared minus R2 squared. So we're going to see this is going to cancel, and it's also times because it's a difference of squares, R1 squared plus R2 squared, and it's still over 4. So we're going to cancel this, and this is going to turn into a 2, and then we're going to cancel R1 squared minus R2 squared term, and we're left with m equals, let me move this, no, not m times R1 squared plus R2 squared over 4 equals I. Now, is this expected? We know this is expected because we should know that for a solid disk, the moment of inertia is going to be I equals m r squared over 2. So what we're saying here is if we set R1 or R2 to be 0, so that means that we only are taking a non-shelled cylinder, or a disk, because L doesn't come up in this final one, we can expect that it would simplify to m R1 squared, or R2 squared, over, sorry, this is 2. So that gives us the moment of inertia of a disk, which is what we'd expect. Thank you.